I'm really impressed over what has been said so far these 2 days. And I mean, we have all come here for one purpose, and there is a few numbers of buildings to cite. And I've been removing slides, I've been adding slides, I've been shuffling slides around, and right now I have no idea what I have in my presentation. And to start with, there is something here, and I don't have glasses, so I'll try my way. I changed the title a little bit. Wood matters for building processes, or wood matters for building processes. And I'll talk a little bit about why we believe in wood and additive manufacturing, and a little bit around it. I mean, we got a Hush Awakening 2009 by Al Gore, and now we have these 17 development goals that we all have to try to fulfill, and it's expressed by RISE as we are working for these 17 goals. And this is something I've used for many years. We want to get from a fossil-based economy into bio-based. This changed. From the beginning, I also used to quote Sheikh Yamani, and we used to say we wanted to go from an oil-free to a bio-based. But as we are making fuel and oils from the forest, we can't say. So it's a fossil-based economy we want to avoid, and we want it to become bio-based. Once upon a time, we had this dinosaurs, but dinosaurs has also become the definition of something that disappears, that are obsolete and not really adapt to the world they are living in. Observe the dramatic sky, and observe the silhouettes of these dinosaurs to be. And I think they are strikingly like, at least I can see the T-Rex in them. And I mean, every day we are pumping, or every second we are pumping 150 tons of crude oil, which is ex-dinosaurs and their nature. And we are trying to 95% of it is burned, 5% is used to make materials or chemicals. But this is our competition if we want to construct and build. Every second we are producing 130 tons of cement, which is then mixed with gravel and other things to become concrete. And it's 130 tons of cement. Each second, it equals 130 tons of carbon dioxide each second produced. And then I sound like a sect preacher when I say that we are producing 3,000 tons of cellulose each second. And cellulose is binding, collecting, and storing carbon dioxide. So of course we should work with cellulose. And I mean, it's not all cellulose that you can find in trees, but trees is a big collector of carbon dioxide and a big source for cellulose. And you saw this, or a type of this. We have the forest. We are making, using round timber, we are making construction timbers, and then we are disassembling it into fibers and fibrils, and we are also using the nanocellulose or the sugars or the lignin, which is the glue that glue the cells or the fibers together, or the hemicellulose or extractives. So we use the whole tree more or less, and especially at Processum you are a biorefinery and taking care of all the parts. And most of these parts can be used for construction. And the question David raised, how do you define wood? And we say wood-based, or we think that anything that we take from the tree, we can call it a wood-based material. And I mean, we got the question about the CLT, or cross-laminated timber. Solid wood as CLT or as timber or as glulam, it's excellent building materials, and they should continue to be used, and they are really excellent materials. And but if we want to go further, we have to replace a lot of concrete or oil-based materials. There is an increased claim for recycling. We have to think, how can we recycle materials? How can we make a cyclic economy out of this? We need to enhance the property space. If we want to replace a lot of materials with cellulose, we also have to give cellulose different properties. We have to produce materials that can do other things. I'm a material scientist, and I would tell you that materials are boring and not interesting at all. But their properties, wow, that's something. So I'm interested in how we can tweak the properties, how we can combine material properties into new combinations where we can replace or make better design, better products than we have done so far. It has to be product driven. We have to do things because we cannot just make things for fun. Of course we can do it, but we have to show others what we can do so that they can find some use of it. And the long-term properties of bio-based materials is tricky. Sometimes you want to compost it, and sometimes you want it to last for hundreds of years. So we have to be able to control it. These are the type of bio-based materials that we are working with. We're working with what we call all cellulose composites. That's sort of binding fibers or sawdust or other wood components together using nanocellulose. We are using nanocellulose in thermoplastics. We are making all kind of interesting things. We are making biocomposites where we put the metal skin on them and we get steel properties at a third of the weight of steel. We make materials that can interact on some kind of stimuli. They will move or change color or shape. And we are making bioplastics. We are making films. We are making all kinds of things. And this is sort of what's already known. Brave new wood. We had a project. We are working on making wood composites that can be extruded. This is what's done with it's Joseph Walsh that is doing the CNC milling. We had a question, why can't we continue with CNC milling? I think if we want to make exciting shapes, change forms, and having another design language, CNC is fantastic. But it's subtractive. And you get a lot of shives. And of course, this is an excellent source for making particle boards that then can be CNC milled and so on. So we can take care of everything if we continue that way. There's happened a lot of things with the computational design and fabrication. This is from Grammatica Kohler in DTH. They have robots that are laying bricks, for example. And this is the biggest wooden roof that has been constructed completely by robots. And it's a gigantic, fantastic roof and ceiling at the same time. And then when I've been asked by our forest industry, is there any future in additive manufacturing? What should we do? And we have Paul Gatenholm and we have the Wallenberg Wood Science Center. They are printing in nanocellulose. They are trying to make spare parts like noses and ears or organs. That's not a big volume, and our industry, sorry to say, cannot handle a few millions in profit. It has to be billions in order to make them understand. So volume, maybe we have the volume in the construction and building part. And we also think that we have to think outside the box. And when I visited ETH in Zurich the last time, it's a fantastic campus. They have cows grazing around the buildings. But this day I found a robotic arm on large feet walking around on the grass. They are going to construct a building using this robot out on the field. And then when we are thinking wooden material, we often think, at least we dream about this rural red cottage living on the countryside. But I mean, this is the future, living in cities and mega cities, and you don't see very much wooden constructions. And you make a much smaller carbon dioxide footprint in a city than you do on the countryside due to transportation and all these kind of things. But if we want to continue to build on this, if we have super light, and we have light and strong materials, we can build on top of the old constructions. Many of the big cities are on river deltas. It's not very good ground. You have to put poles into the ground 30, 40, 50, 60 meters down. If you have lightweight materials, you don't have to. You can construct on land that was not good for building big concrete constructions. And this is the conventional construction. In order to, we saw it yesterday also, even if you CNC the wooden construction, you build a wooden house and you fill it with concrete and you remove the wood, and the wood is then waste, and you have a concrete building. And we just got granted, and we will actually start tomorrow, a project called Woodwood. And it's about 3D printing or 3D printing. That's 3D printing with tree. And it's for the construction and the building. It's ACTSO. And we are coordinating, but ACTSO, it's pulp and performance chemicals. They are taking care of the fireproofing and some performance chemicals. We have Arbio, which is Svensk Trä. They will take care of the communication part and make sure that it's spread to everyone. We have Chalmers, it's the architectural school, which is a lot about the digital part, the digital tools. And then we have a polymer supplier, which we are negotiating with right now. Fredels, it's a do-it-yourself company. They want to look at the business model. What happens if they have a giant 3D printer? If you want to make a balcony or a terrace, you can go and you can have your individual things printed out, or you can repair some furniture if you need a new leg for a favorite chair. It's KTH, it's the Department of Mechatronics and Machine Design. We're going to work with the design of the printer heads. We have Phenotype Studios, who are architects specialized in wood and digitalization. Ragn-Sells, they are recyclers. They want to know how we are producing these materials, how we are producing the artifacts on buildings, so that they know how to take them apart. And then we have the saving company, Scania, because we think it would be very hard to print anything for the building and construction market and to get it because of the standardization things. But printing something for a truck interior is much easier. So that will be the thing that we can show, so that it will not just be that we promise. Then we have Stora Enso, who wants to develop the materials. And then we have Veidekke, which is one of the big construction companies. And then we have White Architects, who are also very interested in the possibilities for new design language and new design tools. And this is some of the studies. We have, just to show the structure, we have architecture and design. Then we have system communication, material development, and printer development, which is really collaborative and iterative. And the problem is that you have the design tools, you have the engineering calculations, and you have the building information modeling system, but they are not communicating. And our new materials do not fit into these systems at all. So there is a big thing. And this BIM system, once it exists, Ragn-Sells want to use it to run backwards in order to deconstruct buildings. And then we have the application, where we will have the car interior and some building elements. And then we have sustainability and deconstruction. And we have done some pre-studies on when it's worthwhile to look on additive manufacturing. We have been looking on this kind of the space frame, on how to do it. We didn't have the Magpie, but we did what we could. We have been looking on how to get what kind of elements can be used when we want to build lightweight structures which we can put skin on. And we have also developed a new printer head where we can print with rope or yarn, which will give us fiber direction. So then we can give materials with... now I'm lost completely. I mean, we can have different properties in different directions, and we can control the strength in the materials in a completely different way. This we have done with both thermoplastics and thermosets. So with a thermoset, that means that we can build the space frame really three-dimensional without doing the layer-by-layer printing. And we have also developed from wood at Rice Bioeconomy, we are making carbon fibers from the lignin. And with this printer head where we have the paper yarn, we can also feed man-made fibers like rayon or carbon fibers, that we will have very strong reinforcement fibers in the material. Because that's one of the big problems when you are printing with these thermoplastic things. And have you done your homework when you were in school? Can you read binary code? It says something like this. Digitalization enables. And we really believe that this is the moment where we can do a lot of things due to this. You have the CAD, the CAM, the BIM, but we have to get them to work together. And that's mainly the biggest task for our project, to make sure that we get all these things going together. And the approach we have in what we call material design, it's research, design, and development. We think it's important that the design part is before the development part, because we need the communication and the discussion. And a material consists of components, and the components are processed in different ways and mixed, which give a structure to the material, and the structure give the properties, and then we have the products. And also it's very important how you experience these materials, as Elvin said. If we introduce materials in the wrong way, and we also think that, and especially Scania, they are thinking about the design that makes the client accept the 3D printed expression. Because if you hide the 3D printed thing with a very expensive surface treatment, you lose a lot of the thing you gain by doing the 3D printing. I thought I had removed this slide, but this is how we work anyhow. You have a lot of desired property. You have a product that you want to design in some way or build a house. And then you have we'll do it like this. You have the desired properties. You have your design freedom. You can choose size, shape, a lot of functions. But you cannot solve all the problems or your dreams only by looking at the design factor. You also need the material structure in order to achieve some properties. And then, I mean, we can spin, we can make foams, we can, as we saw from David also, we can extrude foams, and we can decide which size we want to have on the cells, if they should be open or closed. We can do injection molding, we can do hot pressing, we can do a lot of different things. With the same identical material, we will get very different properties depending on which production process we use. But it's not enough. We cannot get all the desired properties just by having a structure on the material. It also depends on the components that we use to mix into the material. If we want to make it hydrophobic, for example, we need to add something. So there are at least 3 components, if that's the right word. We have the material components, we have the material processing, and that gives the structure, and we have the design to achieve the properties that we are looking for. And all these have to communicate with each other. And if we have a component system, we also want to have a component recycling, especially if you're going to Mars, like we saw earlier. You don't want to bring any waste molecules, so you have to recycle everything. And I understand that I'm late as you're standing up, so I finish with this one.